Good morning, everybody. So my name is Stijn Calders. I'm part of the BRAMS team, and I'm going to talk about the recent advancements in the Radio Meteor Zoo aggregation algorithm. But since I'm the first to talk about the BRAMS project, a quick reminder what it is about. So BRAMS is a network that is using radio techniques to observe meteors. We are using so-called forward scatter technique, which means that transmitter and receiver at two different places. So we have a transmitter in Durbe, about 50 kilometers south of here. And we have at 50 different places in Belgium and surrounding, we have receiving stations. And if there's a meteor in between the transmitter and the receiver, then it reflects on the ionized trail, and we see that in our receiver. This is how the observations from the receiver look like. This is so-called spectrogram. On the horizontal axis, you have the time. On the vertical axis, you have the frequency. So in the middle of this spectrogram, you see a horizontal line. This is the direct reception of our beacon, our transmitter in Durbe. Then you have these slanted lines, these curves. Very long curves. These are so-called airplanes. And so those are also metallic tubes that reflect radio waves. You have these short vertical lines, which are the underdense meteors. And then you have these cloud shape structures, which are overdense meteors. For the underdense meteors, it's quite easy to detect them automatically, but for the overdense ones, it's more complicated because they can have very different shapes. So therefore, we decided to start a citizen science project, the Radio Meteor Zoo, where we ask volunteers to help us to identify the meteors in our observations during the meteor showers. So to have especially the identification of the overdense echoes. And what we ask to the volunteers is to draw a rectangle, a bounding box around everything they consider to be a meteor. In this way, we started 7 years ago with the peak of the Perseids, 2016. And since then, more than 19,000 registered volunteers helped us analyzing more than 40 different meteor showers. Yeah, to ensure a high level of accuracy, we don't ask one volunteer to analyze a given spectrogram, but we ask 10 different volunteers to do that. And these are the bounding boxes, the rectangles you see in red. So these are the identifications by 10 different citizen scientists. And I presented an aggregation algorithm in 2016 in the Netherlands, how to group these 10 different identifications into the green boxes, which we call the consensus. However, there are two major problems with this aggregation algorithm I discovered. So today I'm presenting you two improvements I've made to them. One problem is that the bounding boxes tend to be too large and contain several meteors. This is because the different volunteers are drawing the bounding boxes slightly different. And so in the aggregation algorithm, group them together into one big bounding box containing several meteors. So this is a problem that we have to solve for two reasons. One is that it leads to an underestimation of the number of observed meteors. And the other is that we also want on the longer term to train a machine learning algorithm to automatically detect these overdense meteors. And the better input data you give this machine learning algorithm, the better it will work after training. So how did we solve this? It's a 4-step process. So the first step is that on the whole spectrogram, we remove some of the noise and also the beacon signal. Then we are looking at each bounding box independently and we binarize them, which means that instead of all the different colors, we only keep two colors. Black means it's nothing, and white means there is a signal there. So we have to choose some threshold there. Then it could be that you have in this bounding box, you have at least one meteor, but you can also have these plane tracks. So those we remove using the linear host transform. Why do we remove them? Because they could sometimes connect different meteors with each other. And then in the last step, we have we detect the contour of the meteor using marching squares method. Then a second improvement that we made in the initial algorithm from 2016, we considered all the volunteers to be equal to each other. However, it's clear that if you gain more experience, if you're doing these identifications more regularly, that you are getting better, that you are getting experience. So it would be better to give more weight to volunteers that have more experience. And this is what we do with the volunteer score. How does it work? After we have done the aggregation, we compare the bounding boxes from each volunteer with the consensus. And if they are sufficiently identical, then we promote the volunteer. Then we have some mathematical function to convert the number of promotions into a score. And we are giving a score in between 1 and 2. This you see on the horizontal axis of this figure. So 1 means a novice user, and 2 means a user that has gotten a lot of promotions, so is doing a good job. So you would assume, but you have to check that the expert users are doing better identifications than novice users, and this you can see in the figure at the right. So in the white box are the novice users, and their correlation has a large spread. They are novice users with whose bounding boxes have a good correlation with the consensus, but they are also much smaller correlations than we would like. But if you look at the right side, so the green area are the users or the volunteers who have experience. There we see that most of them have a very high correlation of more than 0.75, although there is one with a correlation which was slightly below the threshold, so somehow he slept through. So coming to my conclusions, the Radio Meteor Zoo Citizen Science Project aims to address the difficulty to detect overdense meteors automatically. 10 distinct volunteers evaluate each spectrogram to increase the accuracy, but then of course you need to aggregate these results from these 10 different volunteers. And I introduced an algorithm for that during the IMC in 2016 in the Netherlands. And today I presented to you 2 major improvements. One is the enhanced bounding box fitting, and the other is the introduction of the volunteer score. Thank you very much. Questions?
Stijn, you have a question?
How quickly do your citizen scientists report their work? Is it fairly quickly? Or do you have to wait several weeks?
How quickly do they report their results? So to give you an example, for the moment, the citizen scientists are working on the analysis of the Perseids 2023. So it takes a couple of weeks for them to process everything. Okay, thank you.
Thank you, Stijn.